Okay, so now let's see what happens when we have identical particles which are indistinguishable. Okay, now to see what we mean, I think it's best to actually go back to what we mean when we say they are distinguishable. Okay, so I'm redoing what we have already done in general for a specific example, just for you to see the difference between distinguishable and indistinguishable very clearly. Okay, so when I have distinguishable particles, imagine that, I know I have a monatomic, well, maybe not monatomic, but I have a pure substance in which every molecule is the same thing. It could be hydrogen molecules, or it could be whatever you like. Okay, so they look the same, they're little circles, but somehow I can give colors to these circles. Okay, so I can paint them different colors, and I could, if I wanted to, evolve the classical equations of motion in time, and I would see, some trajectory of this one, and then some independent trajectory of the red one, and then some independent trajectory of the other one. Well, actually purple, but it doesn't matter. Okay, some trajectory and some other trajectory, and at any instant of time, if I stop, I can still see where is the blue, where is the pink, where is the red, and where is the yellow, okay? Because they are distinguishable. I can label them, I can follow them. There's no fundamental, so of course this may not be practical to do, but at least there's no fundamental physical reason to think I cannot do that, at least in theory, okay? So for that reason, I'm going to label these particles differently. So A, B, C, and D. Okay, they have different names. So out of this is n. This is my total number of particles, okay? Now, imagine I am making my macrostate. I'm filling my macrostate and counting how many different ways I can pick from this set of particles to realize my macrostate. So a macrostate, as you know, you specify how many particles are sitting in energy state n1, and there you go until the last energy that exists. Here I'm going to just write the energies so that you can follow. And you know that each energy level has some degeneracy. Okay, so this is also something we have to take into account to calculate all the possible configurations as we showed before. So let's just do it, okay? Let's imagine that we go to the first one, okay? And this first one, just for fun, let's say it's 2. Okay, so my n equals 4. They are distinguishable. I'm going to use this notation to refer to the particles. Now this n1 is 2, and for that specific energy level, let's say that the degeneracy is 3. Okay, so we're going to work with that. So how many ways do I have to pick 2 particles out of this set of 4? Well, because there are 4, you can do it by hand. Okay, so you can do A, B is one way, but then AC is another way, and then AD is another way, and then B, C is another way, and BD is another way, and CD is another way. But there's no other ways, okay? And notice that I am not counting, for instance, B first and A second as different from AB, or any other one. Like for instance, DC is now different from ZD. That's what I said before, that I don't care about the order in which I pick. I just care about the specific combination of particles I choose. Okay, so we saw before, so these are 6. Okay, we count them, they are 6. But what we saw in the general formula before is that for a choice of n1 particles that go into certain energy, we can choose particles such as this. Okay, so the contribution to the total statistical weight would be given by this factorial and ni factorial. And in this case, this is 4, this is 4 minus 2, and this is 2 factorial. And if you do that, you get 6. So that makes sense. Okay, that's working. Okay, that's good. Now this is the way to choose particles, but then we have a choice of where we want to put our particles. And like I'm saying here, I have 3 different cells in phase space that happen to have the same energy E1. And these are the cells. This is one cell, this is another cell, this is a different cell. So they are different, but they have the same energy. Okay. Now let's see. Let's try to make a table like in the lecture notes, like that. Okay. I will focus on the first choice. Okay, so I know there are 6 of these possible choices. I'm just going to focus on one of them, like the first one. Okay, let's see. If I choose AB, how can I arrange AB in these 3 boxes I have? Okay, I could put them together in the first box, or in the second box, or in the third box, Or I could just split them and not put them together anymore. I could put one here and one there, you know, or I could put them in different order, yeah. Or I could put them like nothing here and then here and there, like that. Or I could put them even in the first one and the last one, and then the other way around as well. So let me just try to compress this thing and make it so that it fits here like that. I'm gonna move it up a little bit, okay. And now I'm going to try to make space here. So this was one configuration and this was another configuration, okay. So how many are they? 9. Is this consistent with what we know? Yes, because we said that this thing is multiplied by g ei to the power of ni. In this case, this is 3 to the 2, which is 9. Okay, so good, fine. So in filling the first energy, E1, which is threefold degenerate, okay, and given that the occupation of this mega cell in the single particle phase space, it's actually 3 different cells, right? Can be done in 9 different ways, but the total contribution to the statistical weight would be 9 times 6. Okay, so it's a large contribution. Fine. Now let's see the same story, but let's see what happens if we cannot distinguish the particles. So imagine that we have the box, and these particles are like this, like that, like that, and like that. They are the same. Okay, so I can really not distinguish them, not even in practice. In theory, in principle, there's no way that I could be able to track down the individual trajectory of every single of these identical particles. Okay, and this is something what happens. It's an alien concept in classical mechanics, because of course you can do that, but in quantum mechanics you can't. Okay, you just have 4 particles there, and they are in a collective state, and this state is going to change over time. But one thing you cannot do is to say, well, particle 1 is here and particle 1 is somewhere else at a different later time. You can't do that, okay? So imagine these particles are moving. If you like to visualize it like this, if you stopped your timer at any other time, you just, you don't know which particle is which, okay? So fine, that's what happens. So to represent that, my sample of particles to choose from, which are still 4, okay, are all looking the same. Now the first question is, again, I have to do the same thing, right? So I have a macro state, right? So it's n1 to nm, and I'm looking at what happens here to n1, okay, which just corresponds to energy E1, and the degeneracy is whatever, right? So this thing, Gm, not m, little m, to be consistent with my notation. Okay, so again, like before, I'm going to say that the degeneracy is 3 and the number of particles is going to be 2. So now the question is, how many choices of identical, indistinguishable particles can I make out of a sample of 4 if I pick 2? How many of them there are? There's only 1, okay, because all choices that I wrote before now are collapsed into the same choice. There's only one choice, okay. So this is the choice part of the thing. Now we have to ask ourselves about the second part, which is how many different ways can we distribute these 2 particles among the 3 different phase space cells that happen to have the same energy, E1. Okay, so I'm going to draw them again, 1, 2, and 3. I make them, let's just try to make a decent table. Like that, like that. I have 1, 2, 4. Yeah. So how many different ways there are? Well, I could put them both in the first, both in the second, and both in the third, or I can put one here and one there, or one here and one there, or one here and one there. Okay, but we have less choices, because before this split into 2 possible different choices, and now both have collapsed into 1, and the same happens to this and the same happens to that one. Okay, so how many of them there are? There are 6. So now the contribution to the total statistical weight of filling in the first number here of the array that represents the macro state is 6, instead of being whatever it was, 9 times 6. So it's a big difference. So how do we write this in general? Okay, this was a specific example. How do we write the general formula for the statistical weight of such macrostate for identical indistinguishable particles? So we write it in the following way. We just have to come up with a way to count these guys. So this is the only part where counting is important. There's only one way we can pick Ni particles out of N if they are indistinguishable, but then we have to figure out how to distribute them between the different cells that have the same energy. And the way to think about this is the following. So let's just try to represent the first state, if you like this. So there are two circles, one line, one separator, and another separator, and nothing here and nothing there. And this state is certainly different from the state where I have one separator, two particles, one separator and nothing, or the state, for instance, when I have one particle, one separator, nothing, one separator, a particle. So you see what I'm doing to kind of represent different lines in this table is really to flip around, to do the permutations of two different types of objects. Okay, so I have two of these guys, and then I have two of these guys. In general, I will have Ni of these guys, and I will have GEI minus 1 of these guys. Okay, and I have to ask myself, how many ways can I do the permutations of all of these objects? Okay, so you know, permutations is just factorial. Okay, so if I want the statistical weight, I'm going to call it BE, you're going to see why in a moment, is Ni plus GEEI minus 1 factorial. But of course we are counting things several times if we do that, because, okay, this is a permutation of all of these objects, but you know, if I permutate this by that, I get the same state. Also, if I permutate this by that, I get the same state. So actually I have to subtract here to remove all the permutation, all the internal permutations of separators, which are all identical, and particles, which are all identical. So how many particles are there? Ni factorial. And the permutation of the separators in each configuration is going to be equal to the factorial of GEI minus 1. So this thing, if I take it for all energies, right? Well, that's a multiplication in all different energies. The degeneracy of each energy level and the number of particles that are in each energy state, that gives me the new statistical weight. And this statistical weight is what I'm going to call the, where is it? This is not writing for some reason. Well, don't know what to say, guys. I have a technical problem here. There you go. So this is the Bose-Einstein statistical weight. What happens for identical indistinguishable particles? And now what we have to do is to calculate the corresponding expression for the equilibrium occupation. So I want to know what these things are if I want to maximize entropy in an isolated system. Okay, and I want to see what's the difference between that and what we got before, this Maxwell-Boltzmann formula. This I'm going to split now. I'm going to make it in the next video.